Okay, we're in chemistry. So I'm going to start out there. We're in chemistry. And I will also tell you we're going to lie to you. Okay? We're going to lie to you, and we're going to tell you in chemistry there are only 3 phases of matter. And we're going to find out that no, that's not true. Because in physics, they told you how many phases of matter did they tell you at the end of physics? Oh, you guys haven't had physics yet. Sorry. Yes, physics will tell you have 4 phases of matter, and then we're going to tell you that's not true. There's an argument. There's a lot of different phases of matter out there. Somewhere between 9 and 16. Luckily for us, most of them we don't have to deal with. Because most of those phases of matter are when things are very, very, very cold as a descriptor. We're approaching 1 degree or 0 degrees Kelvin, which is absolute 0. So most of those we don't have to worry about. Most of those that are in here. So we're going to tell you in chemistry that if you get the question, how many phases of matter are there? We're going to tell you. The 3 that we're going to be working with are solid, liquid, and gas. All right. So I'm going to have you guys think about. So we're going to ponder here. We're going to ponder for a second. I want you to think about a piece of paper. And I notice some of you do not have a piece of paper in front of you to take notes. That is okay. But I strongly encourage you to handwrite notes. Some of you have the ability to type faster than you can handwrite, which I understand. Because when I am actually writing, I will do that. But handwriting out things and taking notes by hand is a way of studying, and it will help you out. So, but I want you to see that piece of paper right now. You're not necessarily going to have to write on it. I just want you to observe that piece of paper. Okay, everybody got a piece of paper that they're looking at? All right. A couple things we know is if we tear that piece of paper in half, what do we have? What? I got 2 pieces of paper, right? All right, don't overthink it. Trust me, don't overthink stuff. You got 2 pieces of paper. If I tear those 2 pieces of paper in half, what do I got? Got 4 pieces of paper. Eventually, though, I'm going to get down way, way down. And this is where chemistry gets a little bizarre because we are going to be talking about things that we do not necessarily see. Okay? Sometimes we can put them underneath a microscope. And in fact, I think I actually provided you guys with a link from the NIH to actually look at microscopic scales of things. And there is a really cool microscopic scale of a sharp edge of a piece of paper. It's really cool because it does not look like what we think of a sharp, clean edge of a piece of paper. In fact, what it looks like is the end of a tree that's been snapped in half. Okay? It's very, it looks like you have a whole bunch of slivers. But eventually we'll get down to that piece of paper to where we've got a whole bunch of slivers. Most of that, if I'm dealing with paper, most of that, what you're going to see on our piece of paper is that it is probably a plant fiber, right? Probably good old pine that's been mulched up into a fine thing. Actually, a lot of our paper is probably made of other paper because we recycled it and made recycled paper. So we've done a lot of that. But I get down to essentially the cellulose from a tree. Those cellulose is an actual macroscopic molecule. You can actually see cellulose underneath the microscope. So you can actually see cellulose. But we know that cellulose is made up of what? What makes cellulose? What makes you guys? Carbon. Yeah, we're mostly water, right? But what makes up water? Hydrogen and oxygen. We got what is it over there at the bottom over there? That periodic table is completely out of date because we have filled up the bottom one that down there. We have something on the order of what 191 sort of chemicals or sort of atoms that are out there.
This is 103.
103.
Yeah, it's on this one.
And the 103 is out there?
Yeah, that's what it says.
Yeah. But that one's out of date because we have filled up the bottom row. Yeah.
Oh, 114.
Yeah. So, so that tells you how many different types of atoms that we have. So cellulose, because it's an organic molecule, is made up of carbon, hydrogen, oxygen. Probably, I don't remember if there's sulfur or phosphorus in there. But if I'm talking organic molecules, we're talking carbon, hydrogen, oxygen, a little bit of nitrogen, a little bit of phosphorus, and a little bit of sulfur. That's usually what we're dealing with when we talk about organic molecules. Or organic molecules, those are the elements that are in there. So cellulose is the bulk of my paper. What else might be in my paper? Oh, we got carbon. Carbon's in my cellulose, got hydrogen in there. The paper that, even though the folks over in Enid can't see it, my paper is green. Most of you guys' paper is what? White. You know how we get white paper white? Besides bleaching out the color from the cellulose, we add a mineral, titanium dioxide. In fact, you eat a lot of titanium dioxide. If you eat white icing, a lot of white icing has titanium dioxide in it. Titanium dioxide, so titanium is another element, and oxygen is out there. So we get those things in there, but we can imagine our piece of paper breaking it all the way down to an atom. Atom is our fundamental building block in chemistry. Okay, the atom is our fundamental building block in chemistry. We're going to be working with the atoms. Now, physicists will tell you that we can break up atoms. Yes, we can. We can get weird things out there. Yes, we can. However, what's special about an atom is that the atom is the smallest particle that's going to have intrinsic properties. Gold is different than copper. Copper is different than nickel. Rhodium is different than carbon. Fluorine is different than something else. Each atom has its own individual properties. It's going to have an activation energy. It's going to have a different specific heat. It's going to behave differently. It's in there. Some atoms don't want to have electrons. Some atoms want to have electrons. And we'll be talking about those. So the atom is our fundamental building block of chemistry. And we're going to say, we're not going to be alchemists in here. We're going to be chemists in here. I cannot convert carbon or copper into gold. I can't do that. Now, we can create other elements, and we know that uranium naturally degrades into other elements. But in general chemistry, there's nothing we're going to be able to do in this laboratory that's going to be able to change nickel into gold. It's not going to happen. So our atom is going to be something that is going to stay the same. And that's going to be our fundamental building block. Now, atoms, we do know, are made up of three different things. They are made up of protons, neutrons, and electrons. The protons and the neutrons are going to be in the nucleus of our atom. And our electrons are going to be circling around. Now, what is interesting is that the electron happens to be a fundamental particle of the universe. So we have not been able to break up an electron and make it into something else. Can't do that. We do now know that electrons are spherical. That happened in about 2017. Electrons are spherical. So an electron is a fundamental particle of the universe. And during the semester, a lot of what you're going to do is play who has the electron. We're going to do a lot of that. The electron is actually what's going to be moving around and what's going to be doing a lot of different things for us. And so a lot of what's going to happen is who has the electron and who wants the electron. So that's one of the things that we're going to be dealing with. Hydrogen is special because hydrogen has one proton in its nucleus, and a single proton is a hydrogen atom. So we do have protons that are out there. Protons can be broken up into quarks, but we're not going to worry about that. A proton is a proton is a proton. Our periodic table over there is ordered by the number of protons in our atom. So hydrogen has 1, helium has 2, beryllium should be 3, or beryllium is 4. Right, beryllium is 4. I should know this because that's how my grandson is naming his sheep. He has 4 sheep, and so they were named hydrogen, helium, lithium, and beryllium. That's what he did. So those are, so the number of protons are what's going to give us our numbers in the in our periodic table. So that's how we're going to actually work with things. The other thing is if I have a neutral atom, an atom that is neutral, it's going to have the exact same number of electrons as it has protons. Exact same number. So a neutral hydrogen atom is going to have 1 electron and 1 proton. A neutral carbon atom is going to have 6 protons and 6 electrons. Now, most of the nucleuses will have something else in there called neutrons. Neutrons do not have a charge. Protons are positively charged. Electrons are negatively charged. And my neutrons are neutral charged. It's the term neutral. So we've got those. So that's what's going to give us in there. Now, a neutron is slightly heavier than a proton, but they're pretty darn close in their masses. Okay, they're pretty darn close in their masses. And that's what we're going to be working with. So those are going to be our basic fundamental building blocks. So we can represent atoms a couple of different ways. Okay, our book will do a space filling here, and a lot of times when it's talking about doing it as space filling, it's showing you an atom, or that space could also represent a molecule. Molecule is a combination of atoms, and compounds are a combination of atoms, which is one of the reasons why I wanted you to imagine our titanium dioxide, because our titanium dioxide is a compound where cellulose is considered a molecule. And that has to do with bonding, although we will refer to them interchangeably. So a solid is going to have an ordered structure. It does not have to have a container. And it's going to typically we use it as a regular type structure. So a representation of a solid that you'll see in your textbook is going to look something like this. Liquids are a little different. They got to have a container. Okay. They're going to be a little more random in their filling of their container. There's going to be a little bit more space in here. But it's going to have a defined interface. Okay. So when I put water into a beaker, we know that that's a liquid. So the solid form of water is ice. The liquid form of water is water. And the gaseous form of water is steam. And our gaseous form is going to be very, very spread out. And it'll be expanded, but you will not have a defined interface. So we can represent our gas, solid, liquids, and gases. So when we represent our atoms, we're going to do it as a space filling type model. You may see them in a variety of other ways. We may also do stick, where if I want to do methane, so here's my carbon, and I can represent methane like this. That will use our atomic symbols and our periodic table. So if I want to have carbon, carbon will have something like this on here. We'll have a 6. It'll give you your symbol for the elements. It will give you what is known as the atomic weight or the molecular weight. You'll hear it both ways. And when we get there, if you haven't had chemistry before, that is the mass of 1 Avogadro's number of carbon atoms. Okay? And Avogadro's number is 6.022 times 10 to the 23rd number of atoms, number of things per mole. 6.022 times 10 to the 23rd. That's a whole lot. That's Avogadro's number. So we will be going through this so we can represent our atoms through a variety of different items and different things. I'm checking our time. Okay. So when we are working with things, we also want to start using our numbers to mean things. So, for example, so we're switching gears a little bit here. If I have a target, I'm going to put 4 targets up here. And I'm going to fire at my target. Oh, let's see. Okay. So I've got my 4 targets in here. And if I were to take the average of my 4 shots, this one would kind of look like it's hit the center of the target. So this one would be considered accurate, but not precise. This one, I've got a really tight grouping, really close to the middle. This is both accurate and precise. This one is precise, but not accurate. And that one's not accurate or precise. So every one of these has a source of error to it. And we are going to be doing a lot of comparison with error. There's 2 things that we can do. We can do a percent difference or percent error. Our percent difference is dealing with 2 numbers. So if I have 2 things that are happening, I get A minus B divided by A plus B divided by 2 times 100%. Percent error is my unknown, and these are absolute values, by the way. Unknown minus the known divided by the known That's absolute value times 100%. So that gives you how good or how this will compare two different measurements. This will compare your measurement against a known value. So this will give you your idea of error. Okay, this will give you your idea of error. This one here, I have a problem. This has got bias to it. Bias tells me my instrument worked pretty well because I got really good precision, but I didn't get the right answer. And there's a whole lot of reasons why I might not get the right answer. So let's look at the difference between bias and our precision. I'm going to go out and I'm going to take the mass of a whole bunch of pennies. And let's say the known value of my pennies, as it comes from the US Mint, is 2.500 grams. Now, just because the writing of my number here gives me a hint to the precision of my number. Every penny that comes out of the mint, it should be at 2.500 grams, not 2.5 grams, not 2.6, but should be that. So this tells me the precision of my number. Now, my penny could be 2.5001, 2.5002, 2.5003, 2.5000, 2.5004. Any one of those, my penny would still be, per the mints, 2.5000. So this is 4 significant figures. The significant figures are going to tell me the precision of my measurement. Doesn't tell me if my measurement's right or not. It just tells me how good my instrument is. Because this is where the error in the digit is. That's where the error is going to be. Okay, and we can have any one of these, and that would still be my 2.5000. We are going to use the rounding that 0 to 4 rounds down. 6 to 9 rounds up. And the 5, we're going to use the engineering version, where if it makes the digit, so if I'm going 0.005, if this digit is even when you round, then round to the even value. That's what we're going to do. We're going to round to the even value. That's not in there. Sorry. So it's going to round to the even value. So what's going to happen is we're going to round up half of the time and we're going to round down half the time. And that is to alleviate bias. So we're going to use that convention so that we're rounding up half the time, we're rounding down half the time, so that we get that's in here. In chemistry, we're going to be very, very persnickety about significant figures, because that tells you the accuracy of your measurement and the accuracy of your experiment. And it is very important when we're worried about accuracy that we keep track of our significant figures. So that's why we're gonna have to round up or round down. All right, so we're going to, so we've gone out there, we've got 100 pennies. And my 100 pennies is gonna give me, if I'm doing this right, my 100 pennies is gonna give me something that looks like this. And we find out that my average is not 2.500, even though we know that the US Mint made us do 2.500, that's where it came out of, that's what we've got. And we go out, we measure 100 pennies, and it doesn't work. I'll tell you this for a fact, you can go do the experiment. It's not gonna come out. It's gonna come out just like this. And I'm gonna ask you why.
Big enough sample size.
I got somebody that says that a big enough sample size. I can make it 1,000 and it's still gonna come out that way.
Let's say the sample size, it's like a 58 sample size, so it's more.
No. But even if I take the bigger and bigger sample size, I'm still gonna have it be above the 2.500.
Because
It is different
they
materials.
measure it only at once.
2.500 is only new ones.
Okay.
Now, if I did only new ones, it'll come out 2.500. What happens to a penny once it hits circulation?
Oxidized.
It oxidizes. So instead of being whatever the total material is, it's now copper oxide. It's adding oxygen molecules, so my pennies actually gain weight. Pennies will actually gain weight. Now, why do I still get a bunch over here? Because we scrape pennies, we chip pennies, we do a bunch of other things, we scrape off edges. You know, they're getting used, they're gonna be worn, you know, they're gonna wear. And so, yes, I will, but on the whole, what's gonna happen is pennies will start oxidizing, they'll start to gain mass, and this is bias. Now, this is not bias because somebody put their thumb on the scale. This is bias because Mother Nature biases things. Mother Nature turns out not to be fair. We're gonna find out Mother Nature's not fair a whole lot of the time. So Mother Nature's not fair, but that is bias. So that is an experiment that gives us bias. Another way that gives us bias, if we go back and we look at that, let's go ahead and take it as a rifle. Yes, when I fired my son-in-law's rifle, his 22, that's the shot pattern I came out with, and I said, your sights are off. Now, granted, his sights were set for him and not for me, but his sights were off. I still got good precision, but because of the way his rifle was sighted in, how he actually configured his rifle, how it was sighted in, he built bias into the rifle. And he built bias into the rifle for him, not for me. My sights would have been set a little differently. Now, what we're going to find is some experiments are biased. They're always going to give you something a little more than it should. Each one of our instruments are biased because that's just the way an instrument is. Each instrument's a little bit different, but we have to account for that bias, and that's where the error is. And that's why we're going to get errors in our numbers and have to use significant figures. Okay, so let's look at significant figures. Let's look at it a little differently. All right. So I've got an arrow here. And I'm going to give you this scale. Then I'm going to give you this scale. And we're going to do this one. If I'm using that scale, just that one, it's not one, right? I can estimate what that is. I'm gonna go ahead and say that that looks to me like 0.9. Because I'm going to do a mental interpolation against my scale to tell you what I think that value is. It's less than 1, it's more than 0, but I think it's closer to the end of this scale than the other one. Now, if I use that scale, I'm a little better, right? I'm a little better because I know it's greater than 0.5. I know it's less than 0.1. So now I'm still going to say it's about 0.90, but I have something there that is allowing me to tell you now that that's where the error is. It could be 0.8, but it's certainly not 1. Now, if I go to that scale, it really doesn't make it to the 0.9. So now I'm going to do my 0.89. I might be able to go ahead and say it's over to 1, but I'm going to base my error off of the scale that I have. So we interpolate a lot of things. So you'll do this with graduated cylinders. You'll go in, and usually what happens is whatever measuring device you have, like a ruler or a graduated cylinder or any of those that have a traditional speedometer where you have a line in there. Anything that's a mechanical device, you're going to do an interpolation and you're going to get that error that's associated with your device. It's usually 1 digit more than what the device reads. If you have an electronic one, like an electronic balance, you record all the digits that the electronic balance gives you. And you guys are going to see in this room when you use an electronic balance that our air conditioner vents will cause that last digit to fluctuate. And so there will be error built into your mass measurement because just the air circulation in the room. And so that significant figure is going to tell us how to deal with the error. Now, what happens when you do a calculation? Okay, when we do a calculation with our error, if I'm adding 0.9 to 1.0, 36.789. I'm adding those numbers together. I'm going to get my 9, I'm going to get my 0, I'm going to get my carry the 1, I'm going to get 7, I get that 1, I get 38.9709. I cannot report that number. I can only report to the same lowest common one, and so I can only report to that. This is with addition and subtraction. Okay, when you're dealing with addition and subtraction, you're using the columns that you're playing with for the numbers. Now, if I am multiplying 0.92 times 101 times 36.789, if I do that multiplication, I'm going to get my calculator is going to give me 33.84588. Well, we know we cannot do that. Okay, we know for a fact we can't do that. I'm going to take the lowest number of significant figures. This has 2 because the 0 is significant. Any 0 that ends after the decimal place is significant. This 0 is just a placeholder. This is just telling you where it is. So that 0 is significant. So this has 2 significant figures. This has 2 significant figures, and this has 5 significant figures. I have to go with the lowest number of significant figures. So my answer in this case is going to be 34 because I'm going to round by 8 and I'm going to get 34. And that's the number I would report with its units, of course, because all of our numbers are going to have units. Okay, so significant figures, when we're looking at them, if I'm getting 0.000386, this only has 3 significant figures. This is a placeholder, this is a placeholder, that's a placeholder. How I can tell is if I write it in scientific notation, it's going to be written like this. It's -4. And that tells me exactly how many significant figures that I have. Now, if I were to write that same number, 0.00038600, this one has 5. Because both of these zeros are significant. Both of those zeros are significant. Now, if I have 10,360, that number, I only have 4 here because that is a placeholder. If I wanted to show that 0 as significant, if I do that, now it has 5 because that tells me that 0 is significant, or I can write this out as and that would tell me that that 0 was significant. So I would encourage you all to review significant figures. In some of your materials, I have some significant figure rules in there, and I think, real quick. I guess your book doesn't have it in this chapter, but you want to make sure that you review the significant figures, because that is going to get you and it'll bite you every time, and you'll lose points in lab, you'll lose points. So you want to take care of that. Chemistry is all about ratios and conversions. Okay. We are going to be doing ratios and conversions throughout the semester. Pretty much, they're going to look a little odd, but we're going to be doing ratios and conversions. So let's do a conversion real quick. Let's do, I'm going to do, let's do 5263 feet, and I want it to go into meters, and I'm going to use the conversion factors in my head. So we're going to do a long ugly one, and we're not going to do one that's direct. But what conversion factors do you have in your head?
1 foot is equal to 30 centimeters.
Well, I don't remember that one. That might be a good one, but I don't remember that one.
That's how I get from.
That's not one I remember. But we all know that 1 foot is 12 inches, right?
Mm-hmm.
Most of us know that one.
Yeah.
The one that I always have in my head, because it is an exact conversion, is that 1 inch is equal to 2.54 centimeters. So your 30 centimeters is probably pretty darn close. Right? And we know that there are 100 centimeters into 1 meter. Now, some of you will remember that 5280 feet is a mile. Some of you can convert between miles and meters. I mean, it's just up to you. You can look up, there's conversion tables. You've got conversion tables in your textbook. We've got a whole bunch of conversion tables, but we're going to use these three. So if I want to get from 52, 63 feet to meters, I'm going to do my 52, 63 feet. And we're going to go ahead and get it into inches here. We know that 12 inches is 1 foot. How do I know to put the foot on the bottom instead of on the top? It's because those units are going to cancel each other out. Also remember that this is equal to a 1. It's a weird 1, but it is a 1. So we're multiplying 52, 63 by 1. We're just converting our units to get us there. And I'm going to go ahead and do this in steps rather than all out at once. Because you can do it all out at once, but I'm doing it in steps. So I'm getting my 52, 63 times 12. That's going to give me 63,156. And now I'm in inches. Now, if I'm reporting inches, the question is this an exact conversion or not? And this one is an exact conversion, so it's considered to have infinite significant figures. Okay. Now, if it's not an exact conversion, you're using the significant figures in your conversion table. But this one is considered infinite. So I would report, if I'm stopping here, I could only report 4 significant figures because that's what all I started with. So I would report 63,156. However, this is an intermediate calculation, so I'm going to hang on to that. I'm going to hang on to my significant figure that I was given. So now I'm going to do my 63,156, and that's inches. And we know that there are 2.54 centimeters per inch. This one is also an exact, so it has infinite. So I got that one. So I'm going to multiply that by 2.54. And now I've got 160,416.24 is what my calculator shows me. And now we're in centimeters. If I stop here, I'm only going to report 160,400 centimeters because I can only report to 4 significant figures. This would be a placeholder, that's a placeholder, and that gives me that number.
Why is it?
Because I started with 4 from up here. I've left the 5 here because it's an intermediate calculation. But if we were going from feet to centimeters, I'm still only started with 4 significant figures.
So you don't go down to 3 because of 2.5 centimeters?
Nope, because that's exact, so it has infinite number of significant figures. As long as it's exact, it has infinite number of significant figures. And it just happens that the 2.54 centimeters is an exact one. Now, if I want to go to the 100, right, we're going to do centimeters. So now I've got my 160. Go ahead and carry all my gory details here. And this is in centimeters. And now I've got 1 meter divided by 100. Now in my metric system, these are infinite. These are exact. So this is now divided by 100. So now I would report, and now I'm going to cut it off. I'm going to report that as meters. Because again, I'm starting with my 4 significant figures. And I've gotten down to my meter. Now, of course, we could have done this all in one step. So let me write it out all in one step. 5, 2, 6, 3 feet. 12 inches. 1 foot. 2.54 centimeters per inch. And 1 meter, 100 centimeters. 1604 meters. And that this unit cancels out, that unit cancels out, that unit cancels out, I'm left with my meters and it's there. Each one of these is a 1, which allows me to do that multiplication. And when you figure out that chemistry is just a bunch of conversions, life becomes pretty easy. All right. I got 2 minutes left. We're gonna stop there. You will get some, and you guys have probably got already figured out what some of the little quick answer questions are gonna be for attendance on Friday, Monday, and Wednesday. And we will go from there, and I will see now for you all on Friday of next week. I would just zoom in. And I'll show you guys when we get back how to start the room so that you can have it up on the screen and you all can get together. But you guys do have a Zoom link on Blackboard and you can zoom in from anywhere. Yeah. A week from Friday.
So just.
We'll be, I will be in the classroom in Enid. See, I teach from Enid on Fridays. So I will be teaching from Enid and I'll show you guys later how to start this room.